Hello, everyone. Welcome to Fortress Power's webinar on pain points of installing lithium batteries and Fortress Power solutions. This is a very special webinar as it is available for a continuing education credit that is registered with NABCEP. To request your completion certificate, please stick around to the end of the presentation. We will provide you with a quiz link to the GoToMeeting chat box, and certificates will be emailed to you within 24 hours. Please note that this webinar will be recorded and a video link will be sent to all participants who stay the duration of the meeting. This webinar is actually sponsored by RENVU. RENVU is a distributing partner, and Fortress Power, they are giving away Visa gift cards when you purchase an eFlex and eVolt from RENVU through today, Wednesday, November 11th. A couple of things to mention. They have a megawatt club in which you can receive free shipping and free permit packages on full system orders, and their solar kit guide tool can help you instantly design and quote off-grid and energy storage systems. They gathered industry professionals in a new LinkedIn Energy Storage USA group to discuss energy storage technologies, market updates, and learning opportunities. You can join the group and stay informed to discuss storage with other industry professionals. And now I'd like to introduce you to our host today, Fortress Power Applications Engineer, John Cromer.
All right, welcome everyone. We're going to go ahead and get started. If you do have any sound or audio challenges, leave a message and as a question or in the chat box that we know you're having issues. Otherwise, I might be talking to myself for an hour and we don't want that. So feel free to ask questions regardless. This is our facility in Southampton, Pennsylvania. You can see the solar arrays that we have on our rooftop. Those are actually connected to our testing lab inside our facility where we have, a half dozen different battery inverters on the wall. We connect them up to all of our battery products to do testing and development, both open loop and closed loop. And hopefully by the end of this webinar, you'll have a better understanding of what those terms actually mean. We also do sales and logistics on the coasts and distribute with your favorite solar distributors. Just as a reminder, you can always email tech support at fortresspower.com with your project questions during development or during the construction, and we will get a prompt answer sent your way. So what we're going to talk about today are some challenges that installers face when installing battery systems in the field, particularly for the first time. This is part of a ongoing webinar series where we are trying to enable our installers to be better at designing and installation and project planning to reduce issues in the field. So today we're going to talk a little bit about battery capacity sizing, inverter charge and discharge settings, as well as some DC battery combiner flexibility, and then also talk about some installation flexibility as well. At the end of the program, I will get to your questions. So David, we will cover that towards the end of the program where we can have more open-ended discussion. Just diving right in, we have this training called the 4 powers rule, and I would say this is not something you need to like memorize or write down, but it's more to ask yourself, when I am sizing a battery system, what size considerations do I need to be aware of, do I need to think about? And of course, continuous output power is the number one thing. You buy an 8 kilowatt inverter, it has 8 kilowatts of output power, but then you also want to make sure you have enough juice in your tank, a large enough battery capacity. You also want to make sure that the system is well designed for maybe some electrical currents that you don't know about. And so we're going to talk about that issue as well as some charging issues to enhance our knowledge of battery sizing. So with that, let's dive right into some spec sheets. So here are some spec sheets on a couple of different battery inverters, and let's just take a quick review to see what we have here. So here we have a battery inverter that says it's a 9 kilowatt battery inverter. And then it runs in an 8 kilowatt mode off grid. So the battery is actually capable of supplying a little bit more in a grid tied mode than in an off grid mode. And we would say, okay, well, you know, when we are putting devices onto this particular brand of inverter, you know, if we put more than 8 kilowatts of load onto an 8 kilowatt inverter, you know, what'll happen? Well, the inverter will enact its own protection mechanisms, and after a period of time, usually about 1 minute, it'll turn off. Now, this particular inverter has a little bit more flexibility put into it. It gives you a little bit more power output when you're grid tied mode. So you could put 9 kilowatts of load on it, and then, you know, maybe a little bit less when you're in the off grid mode of operation. But what I really wanted to point out with continuous output power is that there's some other spec sheet items on inverter sheets that might lend you to think the inverter is capable of outputting more than its rated power. So, you know, we're really talking about an 8 or 9 kilowatt inverter here, but it says, oh, look, it could surge up to 16 kilowatts for 10 seconds, or it can surge to even 25 kilowatts for a tenth of a second. And so sometimes these features are called surge ratings or burst mode ratings. There's a little bit more going on behind the scenes to these surge mode or burst mode settings that is worth being aware of. So we're going to get into that in a minute, but just for comparison's sake, here's a different battery inverter, and this is a 6,800 watt inverter. And what we see is, you know, they don't necessarily have exactly the same thing like a 10-second or 100 millisecond, but they do have a 30-minute and a 60-second. So we can see for 30 minutes, this 6.8 kilowatt inverter can deliver 8.5 kilowatts of power. And then for 60 seconds, it can deliver, you know, 12 kilowatts of power. And so what that means is, you know, this inverter, you know, if you subject it to it's a 6.8 kilowatt load, but if you subject it to 8 kilowatts, you know, it'll actually run for 30 minutes before turning off. You know, this other inverter, you know, it may not be able to run above the 9 kilowatt grid tied or 8 kilowatt off grid. Anything harder than that, it will turn off. And so, you know, actually these two inverters are a little bit closer in terms of real performance than might meet the eye, given that this one can surge to, you know, 8 kilowatts for a short duration. You know, if we look at this maximum output current for 60 seconds and it's 52 amps, well, a volt times an amp is a watt. So 52 amps, you know, multiplied by 240 volts will get you 12 kilowatts. And so what we see is that a inverter that's in the 6 to 7 kilowatt range for a short duration can actually exceed its performance, but it's important to note that this is not for a long duration. You know, the minute that this inverter goes above, you know, its kind of continuous output rating, and this gives you a little bit of wiggle room, but you know, it's usually a hard shutoff. You look at the inverter output rating, you go for more than a minute, it turns off. And so it becomes very important that the loads that you put on your inverter are actually less than its output rating to ensure good reliability and system performance. So continuous power, the continuous discharge rate is a little bit of an easier one. Kind of the biggest kind of gotcha on this is that you look at the AC output of the inverter and it's 30 amps, and you think, oh, okay, well, that's pretty low. You know, if you take 8,000 watts and you divide by the AC side voltage, you know, a volt times an amp is a watt. So if you take your wattage and you divide out your voltage, you'll get your amperage. And so 8 kilowatts on a 240 volt system is 33 amps. The gotcha is that on the DC side, the battery bank is running at about 50 volts, and 50, that's whether it's AC or DC, 50 is much lower than 240, by about 1/5. And no coincidence here, a volt times an amp is a watt. The DC side amperage is 5 times greater than on the AC side. And so, true beginners in these low voltage 48 volt battery banks, so what you have to understand is you're going from a higher voltage on the AC side into a lower voltage on the DC side, and that means the amperage on the DC side is going to be significantly higher than the amperage on the AC side. So often, inverters will list their maximum amperage output, but that's a listing on the AC side. To get the amperage on the DC side, you would say, okay, I'm running at a 8,000 watt inverter. I'm dividing by the nominal voltage of my battery bank, and that gets me to my continuous output amperage capacity. And again, just to repeat, the big surprise here is that low voltage DC battery banks run at high amperage. The grid is relatively higher voltage, 240 volts versus 50, and so the AC output of the inverter is going to have a much lower amperage than the DC side input. And we're going to talk about that a little bit more when it comes to DC combining towards the end of the hour. So let's talk more about sizing for this kind of continuous output power. In our two examples, we're going to do a 18.5 kilowatt battery and a 5.4 kilowatt battery. Now, both of these batteries, it would be accurate to call them 48 volt nominal battery banks. 48 volt is just the nickname for your battery voltages. It's more like a product class, even though the products within the class can have some deviation or nuance to them. So anyway, if you pull open the Fortress Power spec sheets, you'll see that we list our battery nominal voltage at 51.2 volts instead of 48. And it would be conservative to do this, 8,000 watts divided by 48, and that would give you an even higher DC side amperage. But more accurately, perhaps a little bit less conservative, you get you use the nominal voltage. Little bit higher voltage will give you a little bit lower amperage if you need to shave an amp or two out for your wire size calculations. And what that is saying is that the lithium ion batteries, or at least our lithium ion batteries, are the bottom of their voltage range is going to be about 51.2 volts or so. Any resting voltage that's lower than that, you're getting down to the bottom of your depth of discharge. Comparing these two batteries, we got the max discharge current of the 18.5 kilowatt hours, 180 amps. The max discharge current of the 5.4 kilowatt hour battery is 60 amps. And so this gets us into like the minimum battery bank sizes. What is the smallest battery bank that you can put on an 8,000 watt inverter? Well, if this is a 48 volt battery bank, the maximum output capacity of that inverter on the DC side is 156 amps. And so a very common sizing error that we see, especially for your first time installs, is you'll just say, okay, I have a 48 volt battery inverter and I have a 48 volt battery, and so they're compatible. And the shortcut that you shouldn't have taken was ignoring the continuous discharge current rating of the battery. So in this case, we would put, the inverter is capable of demanding, a current that is 3 times greater than what the battery can actually supply. Now, in our case, we have a battery management system that'll disconnect the battery before any damage is done. But on a battery that didn't have that sort of battery management system, you could burn out the battery terminals, you could potentially damage the battery. More often, you'll heat up your battery cables and potentially start a fire by just matching 48 volts to 48 volts and not doing a more thorough design. We also have some short duration ratings and the like. But what I just wanted to focus on for this slide is it's very easy to do a quick sanity check. If you know your inverter size and you're using a 48 or 51 volt battery, you can quickly find out what the DC side amperage is and go and check your battery amperage rating and use that to determine your minimum battery size. So we were looking at just doing a down and dirty sanity check to make sure that we got the DC side amperage being within range of the battery output power. But again, it's incredibly common to have the installer just buy a 48 volt battery and then go out and buy the largest inverter they can find, and that can result in a mismatch between the smallest battery size and the power capability that the inverter can deliver. And this is also a reason why we put a lot of emphasis on closed loop programming, because there's a large customer base out there, particularly those who are not losing power frequently and therefore having to live with their systems in an off-grid mode of operation frequently, but instead customers who just want the batteries there for some time of use metering or some rate optimization, and they only want a little bit of backup power, not a whole bunch of backup power, a couple of hours of backup power rather than a day's worth of backup power. And what one advantage of closed loop communication is that normally in our example, if you take a 60 amp hour battery and the inverter is capable of drawing 156 amps out of it, then you would need 3 of these batteries to stay within the spec of the battery inverter. But in our first kind of introduction class, we mentioned that actually lithium ion batteries are capable of a faster rate of charge, faster rate of discharge. The problem is if you don't watch your cell voltages closely during those times, then it can result in a lower life for the battery bank. You go and read through our product warranties, it shows if you run the battery in a harder mode of operation, it can diminish the cycle life of the battery. And so if you are just taking a random battery off the shelf and a random inverter off the shelf, and you're doing all of the controls based on the battery voltage, and the inverter is reading the battery voltage off the battery terminals and doing its charge and discharge settings based off of that, that's what we call open loop. And to some extent, that is less controlled than if the battery has a computer and it talks directly to the inverter. And so here we have an example of closed loop where for this particular inverter manufacturer, they have a BMS setting, and our BMS in their system is number 4. And when we go and use their BMS setting on this number 4, it knows that, okay, I'm using the inverter with these batteries, and that actually allows us to say, well, you know what? Normally with open loop, we need 3 of these batteries. but since it's using closed loop communication, we can do 2 of these batteries. And so if you're trying to design a system to have the least amount of storage capacity possible, which would imply, the least amount of project cost possible, selecting a closed loop inverter with one of our batteries, and right now Solarc with the eflex is what we're furthest ahead on, can diminish the minimum battery size. So what I would say is if you're used to installing 3 eflexes with an 8 kilowatt battery inverter, from time to time check up on our status of closed loop, because you might find that the smallest warrantable battery for your design has shrunk as we get more closed loop communication online. Even when you look at closed loop, a lot of installers say, man, I really want closed loop because that means I don't have to program the inverter anymore. You still want to go through the process of programming the inverter, even though technically the battery management system is overriding those communication protocols in case the battery management system were ever to lose connection with the inverter, which could easily happen with inverter manufacturer firmware upgrade. So you still, even if you're doing a closed loop communication system, you still want to go through and program the open loop settings. So we do, Bill, on your question, since it's on topical, why does it matter if the max inverter input spec is higher than the battery discharge spec? And it would be the max inverter. Isn't the battery going to discharge based on the load, not on the inverter max input spec? So the answer is yes. What an inspector is going to look at is they're going to look at to say, okay, well, if this inverter does run continuously at its rated maximum output, is the system designed within spec? And so if you put a 12 kilowatt inverter on a battery that is half the amperage of what it should, and you only put half a 6 kilowatt load, then the battery might operate fine. But as soon as that load then gets increased, the inverter is not regulating it, and you can have more load on that inverter than what the battery is capable of, and the battery cables at the very least heat up and cause a fire. So if you're watching the battery amperage output capability, you're not going to run into the mistake. The mistake is made when installers just look at voltage and don't look at DC side amperage. The other problem you might have with putting way too large of an inverter on way too small of a battery is this concept known as inrush current. And when I think about inrush current, I think about short-term loads that are shorter than continuous output. But we have to be a little bit more, we have to take that a little bit with a grain of salt, because National Electric Code says a continuous load is a load that's sustained for 3 hours or more. Now we have these other load ratings on the inverter that say it can go up to, it can increase its output by 50% for a half an hour. We also have these 1 minute ratings for the inverters that are even higher than that, and these 10 millisecond ratings that are even higher than that. Traditionally, inrush current refers to, millisecond loads, or maybe up to a 5-second load. So an inrush current would be very short duration. But what is that? Well, inrush currents are when you have large capacitors inside your device that need to dispatch power for a very short period of time, like starting up a motor, or in solar speak, our inverters. Our inverters have large capacitors in them to suck up that DC electricity and carefully squirt it out into the electrical system in a nice refined AC sine wave. And so we're storing, we're storing a good amount of power for a very short period of time and dispatching it over an interval that could be measured in milliseconds. The same capacitors that can discharge that electricity quickly will also suck up electricity quickly. And that can cause, for the very first time, when you're turning that inverter system on and those capacitors are empty, that inrush current just naturally flows into those capacitors and charges them up. And so you get into inrush errors when you are turning equipment on for the very first time, whether they be charge controllers or inverters, as well as other inrush instances for loads, like when a well pump is starting for a very brief period of time. And so you could go and say, all right, for this example, we have a surge rating of 310 amps, and our battery surge rating is 130 amps. And so we'll need 3 of those batteries so that the battery matches the surge rating of the inverter itself. And so you can run into a problem with too small a battery, really a missized battery, too small a battery on too large of an inverter, even when you don't have the load of the full capacity of the inverter. You could still have the capacitors inside the inverter that when you turn on the load for the first time, they absorb so much inrush current that it triggers an error in the battery management system. And so really where we see that error occur is when you have multiple, in this case with AC coupling, multiple inverters. You could also have it on the DC side with DC coupling, where you have multiple charge controllers. If you turn them all on at the exact same time, with just a second in between, each inverter, flip, 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 versus flip, wait a few seconds, flip, wait a few seconds, flip, wait a few seconds. One will have the inrush currents overlap, the other will have them staggered out. And so in particular, when you're doing systems that have multiple AC coupled inverters, multiple DC coupled charge controllers, in particular on a battery that is only supposed to back up the home for not a day, but a couple of hours, you can trigger a inrush current error. And the solution for that is just to go a little bit easier at startup, turn the inverter systems on one at a time with a period of in between, rather than turning them all on, within just a second or two in between. And so there's another kind of inrush current. Yes, some loads, some well pumps, have incredible inrush currents that are 3 to 5 times their normal operating load. And that means if you have a motor like a well pump, you look at it and it's only supposed to be running at 2 kW, it might have a 6 kW or 8 kW, startup load, and you need to make sure your battery is capable of supplying that as well as your inverter, for that matter. You also have what might be called inrush currents because it's not really continuous output capacity, but I would call them short duration loads. Loads that are measured in minutes rather than seconds, that you also have to be on aware of or on the outlook for. And so installing a consumption meter to locally, not just relying, maybe your utility already gives you 15-minute interval data or hourly interval data. Putting a consumption meter inside your electric service panel to know exactly what's going on with your electricity is always a good idea when you're dealing with solar battery systems, because you can see that there are certain loads, namely well pumps, that can spike up rather quickly. And particularly if you're already operating at the top of your inverter capacity and that well pump turns on, that can trigger an error depending on the internal architecture of the units. So often with higher end components, you don't have the same issues as you would if you're using a lower quality battery inverter, for example. We do have a chart in our dealer resources. So for installers, we've started to develop a dealer resources library. So you can fill out what we call the installer dealer application. That's not the same as being a distributor and meeting minimum purchasing quotas. Our installer dealer application is really for installers. You can find it on our website. That gives you access to a special portion of our webpage where we build resources such as this to help you kind of flesh out what your starting watts and running watts would need to be. So Pete, you have a question. Can the Fortress BMS be damaged when it disconnects? High voltage, overcurrent, temperature. Yeah, I can't get too much into the internals of the Fortress BMS, but what I can say is, it is slightly different depending on which battery you're in. Maybe the eflex has a higher inrush current rating. It's also a little bit more of an expensive battery, whereas the eVault may handle inrush current on a differently, and that is more of a better approach for when you're getting into 18.5 kilowatt hour batteries versus 5 kilowatt hour batteries. And so it's going to be different on each one, but the goal is that the BMS protects the battery. And you say, well, can the BMS itself be damaged with high voltage, overcurrent protection, and temperature? And the answer is yes. That the result of saving the battery under normal operation, the BMS is going to be fine. But when we get phone calls with I had a customer on a BMS board that is more of a legacy product where their battery was at the very bottom of its voltage range and they were running a very high load on the battery, not enough to trigger the low voltage cutout, but more than what they should have the system was very oversized with too small of a battery to begin with, and the result was the battery management system took the current and it burned up. So yeah, there is an element of the BMS sacrificing itself to save the battery. That brings up another good point in terms of serviceable parts. Many solar installers will bemoan the fact that if a chipboard on an inverter burns up, many inverter manufacturers will say, oh, you just have to replace the whole unit. Our systems, while I wouldn't say that they're very easy to field service, we do provide technical support to the installer for replacement parts and field servicing so that when you do encounter an issue, it doesn't require having to purchase a whole new battery all over again. So we do keep spare parts in our Southampton office, and we do kind of select our components and design our systems with serviceability in mind. And you'll see that just continuously improve as the years go by. For picking out the right battery capacity, it gets better with practice. But a lot of times, if you just have, say, 12 months of electrical bills, it's not going to tell you a whole lot about how the building itself uses its power, but you still know what, end of the month consumption figures are. And so you want to know if you know what your end of the month consumption figures are, you can back that into, average kilowatt hour use per day. And of course, sunny days versus cloudy days are going to differ, but that's it'll average out. And likewise, if you know how much energy you're using on average during the day, you also know how much energy you're using on a given hour. And while that number is going to vary wildly, a home might be using 1 kilowatt of power for 20 hours a day and then surge up to 20 kilowatts for 10 minutes when the tankless water heater turns on and drop back down. But for determining battery capacity, if you have your month by month printout, you do have at least an estimate of, on average, how much energy am I using per day? On average, how much energy am I using per hour? And you can take a PV Watts printout, go to pvwatts.com, do a solar performance estimate, and get your hour by hour printout for every hour of the entire year, how much is your solar array producing? And so if you know for every hour of the year what your solar array is producing, and you can kind of guess, on a given hour what your average home demand is, from that point you can say, okay, I'm going to guess my battery bank for going completely off grid is I need 120 kilowatt hours. And then for the month of January, every hour I'm subtracting 2 kilowatt hours, and then I'm adding back in what PV Watts tells me I should be up to a maximum of what my guess was. I guess the battery bank should be 120 kilowatt hours at midnight and at 1 a.m. and at 2 a.m. and at 3 a.m. I'm subtracting out 2 kilowatts per hour, and then when my PV Watts data shows the sun coming back up, I'm adding that back in until my battery is fully recharged. You can start kind of sketching out the the energy use of the battery. In an off-grid setting, it really looks like this. Every day on off-grid, you want that sun to charge the battery all the way back up at the top. And in off-grid, to have reliable electricity, there will be times when your solar array is productive and your batteries are full, and you have what's stranded or unused energy at the top that's just sort of wasted or held there in terms of voltage potential. And maybe later we'll do a class on off-grid sizing or off-grid battery banks. Shafiqua, for your sound issue, I think someone else is just going to have to I think it's on your end because we're not getting too many sound reports on other ends. But what I wanted to point out with this slide in particular is, there's a couple of different approaches to battery sizing, and the first is to say, okay, you want to have this 20% reserve capacity. And so if you start at 120 kilowatt hours and you're subtracting out your day-to-day load and you're adding back in your day-to-day production, ultimately you're going to get into a period where the sun doesn't come back up. And so for off-grid without a generator, you'd plot out your entire PV Watts data for the whole year. You'd subtract your consumption data for the whole year, and you'd look at that minimal amount and say, okay, well, I want to have 20% left in the tank, and that's my good battery size. And then if you go with a generator, you could say, okay, well, actually during this time frame, I'm going to have my generator click on, and that's going to get me back up to the top here. And so I run my generator at that time, and now my graph looks, like normal, and we avoid this period. And so I might just look, for lithium ion with a generator battery bank, instead of having 3 or 4 days worth of storage, I might just look at what my load is during my heaviest period of use. That could be the summertime, that could be the winter time, but I might look at what my 1 day of heavy use is and then have 20% remaining, and then say anything below that, that's a time when my generator is going to kick on and play free safety. And then lastly, we get into, really what the main market is for lithium ion batteries today is not trying to get people to live completely off grid, but try to have them be grid tied. And at which point that becomes a shorter duration power outage. And it might be even smaller if you say, I'm not trying to back up the whole house. I'm just trying to back up. If you ask your customer what they want to back up, they're going to say, I want you to back up the whole house. And even, I'm from Texas. So even in Texas, if you say, well, what do you want to back up? The customer is going to say air conditioning, which is not impossible of a load to back up, but it's a big project. But recently, a hurricane hit, and in my town, it took out power for over 2 days. And, what people really wanted during that time was a little bit of power to charge their phone, power for the internet to be used, and then power for the refrigerator to not have the food spoil. And so at that point, you can get into very small battery banks that are more affordable. And while it's not everything that the customer wants, it does cover their critical energy needs. Normally, you want to be very respectful of what the customer wants, but when it comes to designing backup energy systems, reliability is important, and scaling the scope back to have a reliable backup system is generally the better way to go about doing it. So lastly, we get to charging power. And this is another one that gets a little bit tricky because we provide integration manuals on our website that will tell you, what settings to program the inverters for, but there's still going to be settings that are going to be custom to your job site. And so what you need to be, when you're looking at charging power, what you're looking at is what is the maximum amount of amperage that will go into the battery. So almost the opposite of looking at the discharge rating of the inverter and the discharge rating of the battery, you need to say, hey, I have 2 eVolts, and each eVolt is capable of 180 amps. And so my maximum charge rate of it is 360 amps. And so if I have a 100 amp charge controller and another 100 amp charge controller and a 100 amp inverter, all 3 could be on at the same time, and that's not a problem. So in the off-grid setting where you have very large battery banks, you're not too concerned about having lots of charge controllers and lots of inverters because you also have lots of batteries. It's when you get into a smaller battery, shorter duration battery that might only back up, a whole house for a couple hours, that's when you have to start looking at, okay, if I'm doing charge controller charging with a solar array, AC charging with a solar array, and grid charging with a grid-tied battery inverter, what is the cumulative effect of all the charges happening at once? And you could say, well, I want to charge either from my charge controllers or from my battery inverter. But the question is, so do you have it programmed to prevent the 2 resources from contradicting each other? So that's where you might want to have the grid charge come on only at very low states of discharge so that, to get you through, in an off-grid setting, you don't want the generator to click on every single day. You want enough storage to get you through so that the sun can come up and charge it, reduce your generator consumption. But the concern is when you're grid tied, if you make it all the way to 4 or 5 a.m. and then the grid says, okay, your battery's depleted and I need to turn on and charge, and you start charging with your grid side, and then the sun comes up and your charge controllers go on full blast, could that result in an overcharge situation. And one solution to that is to throttle down the grid charge, to say the grid doesn't need to charge my batteries so quickly, so I'll dial it back. Another solution would be to program the inverter to only charge at night so that it can't conflict with when the charge controllers charge. You know, in fact, wind, you know, our renewable energy cousin, is a little bit more difficult to integrate into the systems because it is so unknown and unmanaged on when the wind is going to blow and how fast those bursts are going to be. Whereas something like solar charging, you know, you can assume that that's only going to happen during the day. You can program the grid charge to only occur at night, and that will buy you a little bit more wiggle room. And so some questions to better understand your system is, you know, what is the maximum charge that's going to be placed on the battery? You know, if my generator is substantially larger than my battery inverter system, if I'm running a 5 kilowatt critical load panel with my battery system and I have a 20 kilowatt generator, you know, how is the charge to the battery going to be regulated? I mean, normally it's with an inverter charger or battery charger so that it is regulated. But you know, I guess the key takeaway to think about is the battery going to be charged by more than one charging resource at the same time? If so, what is the combined total of all those charging resources together? And is that within the regulation of the battery? Or do I need to do some things to prevent these charging loads to occur at the same time? Let's move on into our program. So that gets us into inverter and charger settings. And what is a little bit confusing is from manufacturer A to manufacturer B to manufacturer C, they may have slightly different terms for their charge cycles. So, you know, traditional batteries have a bulk charge, an absorb charge, and a float charge. But whether or not those are all specifically called out as bulk, absorb, and float in the inverter settings is a little bit weird. And you know, and lithium ion batteries are a little bit different than lead acid in that they don't really use a 3-stage charge cycle, bulk, absorb, and float. They really use just a more simple 2-stage charge cycle, which is, you know, a fast bulk charge from a low percent state of charge up to near the top, and then a more gentle absorb charge to get those cells all the way to their fullest potential. And so when you're programming your inverter settings with our batteries, it's very common to disable the float and just say we're going to do a bulk and absorb charge but no float. Well, some battery inverters won't let you disable the float. We don't use an equalization charge on a sealed battery. That's not completely true. There are specific instances when we use equalization to say reset the calibration of the onboard battery management system computer, but that's not like a regular maintenance equalization charge like you would apply to an unsealed lead acid battery. And so regardless of what inverter you're using or inverter setting you're using, what you're looking for is kind of a 2-stage charge cycle, a bulk stage and an absorb stage, and you're trying to disable everything else. Now, our batteries, and this is going to vary from one lithium chemistry to another, and maybe even from the same chemistry from one manufacturer to another, depending on how the internal battery cells are wired together. But for our batteries, we're all at a 54.4 volt charging voltage, whether or not you're applying a constant aggressive charge at high amperage and bulk, or a lower amperage charge at the same voltage with absorb. We're pretty much at 54.4 volts regardless of the charging cycle. When we do that strange equalization for resetting the BMS calibration, we're going to go at a little bit higher voltage than that. If we're doing a closed loop communication, we'll be going at a little bit higher voltage than that as well. But for programming open loop, you're essentially programming all the voltage charges to be 54.4 volts. For that float charge, if you can't disable it, you put in 54.4 volts. Maybe try and look at the timing. For equalization, if you can't disable equalization, you're putting in 54.4 volts and then maybe setting the equalization time to 0. But on our website, we have these integration guides for each battery and inverter that will tell you the open loop program settings. But the short of it is you're programming, the bulk voltage, the absorb voltage, the float voltage to 54.4, and then disabling float, disabling equalization. You can check what the currents are for the batteries for your maximum charging currents. Another common one is to remember that this is a per battery rating. And so if you have 1 eVolt at 100 amps per battery and it has its max bulk current, then you would have, if you had 2 eVolts, then the max bulk current would be 200 amps rather than 100 amp. Likewise with the eflex, if you just go and you put into your setting 100 amps and you have 2 batteries, the battery's going to charge a lot more slowly. This is a per battery current. Some inverter manufacturers, instead of doing a maximum charge current, you have to do a maximum charge rate percentage, where you basically do the same thing, but you divide by the total capability of the inverter supply to get not the charging amperage, but the charging amperage as a function over what the inverter could theoretically supply as a percentage. Let's see some other terms on here. Our default battery temperature, we generally let the temperature controls be governed by our BMS systems for the eflex and the eVolt. And so you generally do not do a battery temperature sensor with our products. Things like the grid support voltage or the recharge voltage. The grid support voltage will be at, if the battery is over this voltage, sell back to the grid. The recharge voltage will be if the battery is below a particular voltage, recharge from the grid. And so, that can just, it's very hard to say what is the state of charge of the battery when you're just measuring voltage and you're not doing a computer-based tracking of every single statistic about the battery to compute a state of charge. And so with open loop programming, we're basically saying voltage controlled programming, and you're programming in setting by setting. Now these settings should not differ from one inverter to the next if the inverters are similarly sized. There may be a slight nuance or terminology difference that comes out of our testing, where we say, oh, this inverter charges slightly harder than the others. So you might see a slight difference between one or the other. Nothing that's going to be a deal breaker. By and large, we're saying program at 54.4 volts for your charging. Set your absorb time equal to 1 hour. Low battery cut in, low battery cut out. These are features that you program on the battery inverter, and then there are also features that are within our battery management system themselves. And so you can program the low battery cutout for, you know, your battery to turn the inverter off before our battery management system clicks in. You know, the nice thing about a battery management system is if you mess up one of these settings, you know, our battery is going to protect itself. A battery without a battery management system, you're, you know, relying on the inverter to be programmed correctly in order to protect the battery to its fullest. And this also might require some custom adjustment to you, where these are more guidelines, which might need to be toggled. You know, if your battery is slightly undersized and you're doing a full cycle every single day, and you're just, the battery turns on to grid charger at 5 a.m. and you're like, man, the sun's coming up at 6, you know, you might dial back the low battery, you know, the grid recharge voltage, you might bring down from, you know, 51.5 to 51. You know, and there's also high battery cutout voltages to prevent the batteries from overcharging as well. So, you know, generally when you have an issue with one of our batteries, the battery will simply not turn on, and it'll be protecting itself because it's seeing, you know, too low a voltage to run loads, or vice versa, too high a voltage with some aggressive charging. Let's see. You know, grid support mode, that's selling back to the grid at a high voltage. These are going to be kind of customer specific settings. You know, some customers don't want to have a grid charge. They just completely disable the grid charge and wait for the sun to come back up. You know, what we suggest doing is setting your recharge voltage, you know, right at around our nominal voltage of that 51.3 to 51.2. You know, that'll be around a 80% depth of discharge or 20% state of charge, so that that battery just operates from its 20% range to its 80% range on a regular basis. Maybe I didn't talk as fast in this webinar, so we're going a little bit over in time. This is our first time through, and we're doing a repeat of the webinar next month. We are making associated handouts and transcripts to go along with this presentation. So if you have to duck out early, we do have a recording for you. We will have manuals for you. You know, just send us an email at techsupport@fortresspower.com. Or go ahead and sign up for our installer dealer resources. But for those who can't stick around for just a few minutes, let's talk about some battery combining solutions. So this is a common issue with our eflex battery, which is a smaller battery. If you're installing multiple batteries, you have to wire them together, you know, or our larger residential or commercial customers maybe paralleling a bunch of eVolts together. So this is a solution that is a bus bar inside a gutter. I can tell you that this solution is common and that it works, but you might be thinking, well, is it going to pass inspection? And it really depends. Now, a bus bar inside a gutter is in an enclosed raceway. You are allowed to put bus bars inside of gutters. The real question becomes, well, is that bus bar, you know, listed for purpose or not? Because in a tough jurisdiction, you know, they're not going to look so kindly upon you, you know, borrowing from one application and using it in another application. You know, the inspector will say, well, has that bus bar been tested for power distribution? And, you know, the problem with most bus bars that are, you know, physically adequate is that they haven't been used in the industry for power distribution like we want to use them in the battery industry or the solar industry. So the bus bar that we just saw pictured is technically, when you look at its UL listing, it's called a grounding bus bar, and an inspector would look at that and say, well, this bus bar has only been tested for use as for grounding purposes, and being served to land all your grounds on, not as a power distribution block. And so I would caution you against just buying generic bus bars to save money in areas where you're going to get a thorough inspection, because you could fail inspection for that reason alone. The bus bar is not listed for use. And you pull open ILSCO's spec sheet on these things, and the bus bars don't have amperage ratings. They don't have voltage ratings, because ILSCO has not been listing them as for power distribution. So they're not going to give you that rating anyway. And so, you may have to, suck it up and recognize that, the DC side components do cost money. High amperage components do cost money. You're going to have to buy more than just the battery. But sometimes building your own box, putting the bus bars in a gutter rather than in their own box, those things can simplify the job site. So, as far as bus bar ratings go from a manufacturer that will give you an actual voltage rating and amperage rating, Midnight is a very popular one. Here pictured is a 1,000 amps bus bar for $133. One item that I would caution you about is buying bus bars from the marina industry. So it's very, if you're looking for cheap disconnects, cheap overcurrent protection, cheap ways to parallel batteries together, there's other markets that have these problems. And so you might find something that looks like it'll fit the bill. You have to make sure that the voltage ratings are also correct. Kind of the opposite of what we had earlier with battery inverters and batteries giving you voltage ratings, but you having to calculate the DC side amperage on your own. A lot of the smaller marina type stuff, the components may only be rated at 12 volts, and you're running it at a 48 volt application. And so they're doing that bus bar rating based off power at 12 volts, not power at 48 volts. And you might find that those cheaper components that are only listed for 12 volt or 24 volt application do not have the same amperage rating when you're running them at 48 volts. And so I would just caution you against getting too cheap, looking for listed parts that are used in other applications, because you might find that that application is a 12 volt application, not a 48 volt application. So it's harder to avoid buying the specialty stuff. But the one component that I don't see a lot of installers using that I think they need to be more aware of is this component that is called a power distribution block. And it is designed to go inside a wide gutter or a metal termination block. And like the bus bars, they have these insulated fittings that can get mounted into the box. And then, you'll get a listed terminal. Sometimes for parallel wiring, you can have your smaller battery cables come in one side and your larger combined battery cable come out the other side. We have one for our positive side, one for our negative side. So you can find a lot of range in listed products in these power distribution blocks, not necessarily a bus bar, but something that's rated that will combine your battery amperage into one combined output to go back to your battery inverter. So take a look at power distribution blocks if you're having trouble combining your batteries together. They do make these nice components called ferrules that will make sure that your thick battery cables land inside those terminals in a workmanlike manner with insulation around the sides, because obviously these things can get pretty close together. I wonder what was in that slide. Yeah, and so in this other slide, we're showing, you know, if you combine a power distribution block, the one thing that doesn't have is overcurrent protection. Terminal blocks for overcurrent protection, fuse holders, fuse blocks are a little bit easier to come by. You know, heck, you know, a knife switch disconnect will often have a fused option for holding fuses. Now, our batteries, inside their battery management system, they do have fuses for, you know, overcurrent protection or inrush current to make sure that, you know, if whatever the installer does gets back to the battery, that the component that fails will be part of our battery management system and not the battery itself. And so some installers have arc faulted during installation, and then they have to open up our batteries and do some field servicing, or some of them mail the batteries back to us and we'll service them here. To avoid having to get inside your battery to do servicing, you may want to add, you know, a fuse blocks and some external overcurrent fuse protection. We've taken it out of our installation manual because if you put something in the installation manual and it's an optional step rather than a mandatory step, you know, not all inspectors will view it as an optional step rather than a mandatory step. But by taking it out of the installation manual, you know, that does also remove with it the fact that it is a good idea to install additional overcurrent protection. So when you think about it, you know, you have to have a gutter to get your cables back to the battery inverters. You know, putting in terminal blocks inside the gutters to do your combining is not a bad idea. You know, before you get to that, you can put in, you know, basic fuses for blowing in an overcurrent protection instance without breaking the bank. You know, these A&L fuse holders, you know, they only cost about, you know, 10 to 15 bucks each, and they'll, you know, only blow during a overcurrent protection scenario, not something like a ground fault or a short circuit or an arc fault. But they would save you the job of having that fuse blow instead of the one inside our battery bank, to make the servicing side a little bit easier. Still a very rare circumstance, and so many installers will just go ahead and skip over that step. And so the last kind of option is to go ahead and buy, you know, these battery combiner boxes that, you know, Midnight has developed one, Outback has developed one. But looking inside the box, now we can see, you know, okay, so they're buying these insulated bus bars to be stood up off the box, and I can buy a power distribution block instead. And they're using breakers, which are really nice to have that nice on-off, you know, breaker. You know, this might actually be a touch-safe fuse holder instead. And so you can put in your own insulated fuse blocks and terminal blocks into a metal box and save a little bit of money compared to the nice, you know, package solution, manufacturer provided solution. So why would you want to build your own box rather than use these manufacturer breaker boxes? Well, many battery inverters now are starting to put breakers, you know, right into the battery inverter itself. And so if you already have a disconnect on your battery circuit and you already have a disconnect on the battery itself, then you might not need all of this complicated, you know, battery combining material. You could probably get away with, for many instances, especially smaller residential systems, just using the provided disconnects on the batteries and breakers, saying, the inverter is already providing overcurrent protection, and so and the battery itself already has a disconnect switch, so I can disconnect individual batteries. I can disconnect the battery inverter. The inverters and the batteries have all the disconnect switches I need. The batteries and the inverter itself already have the overcurrent protection that I need. So all I really need to do is just combine the batteries together, and that's when you would use a power distribution block inside a gutter or a bus bar inside a gutter, just to simplify your paralleling of your batteries. And so, yeah, Drew, it's true. Every connection is a failure point, and in general, you want to reduce those failure points. But in general, when we're talking about connections being put in a box, many installers will say, it's worth adding an extra connection to put a fuse in line. We're not going to go out and say you have to mandate it. If you don't, it's very rare to have a fuse, a fuse blow in this type of instance. The only one maybe we've had a few hundred eflexes being installed in the last couple months, and we've had one blown fuse that occurred on the DC side of a charge controller wiring that carried all the way into the battery. And the takeaway was the installer, first off, we had to ship them kind of a specialty fuse that you just can't go and buy the fuse inside our eflex off the shelf. And then they had to take this cap off and then put the fuse into the battery. It's not an impossible thing to do, but it would have been a lot easier to have an external fuse inside the raceway that they could have installed. Here's a nice video on YouTube that goes through an eflex installation. We're already over time in class, so I'm not going to cover the whole thing, but basically, you get into that and you can see he's putting these bus bars inside the gateways. And then another nice thing that he did was, these cables between the eflex and the bus bars, he pre-made them in advance and cut them all up to be the same length, so that the cable runs between the bus bar and each individual battery are the same length. It's not that the batteries are all located the exact same distance from the bus bar, it's that the cables to connect point A to point B are the same distance. So the last topic before we get into questions is installation flexibility. And the main question with regard to our products is, well, do you use the eflex or do you use the eVolt? And with the mindset that every connection you make is cost and a potential failure point, and you get to the point where the eVolt is the more cost-effective default battery, simply because of its size. It's 18 kilowatt hours instead of 5 kilowatt hours. They're all machine welded inside that battery. Fewer connections, fewer parts, more capacity, results in a lower cost per kilowatt hour compared to the eFlex. And in fact, the eVolt, being 18.5 kilowatt hours, it's designed to kind of skip all the combining and say you can just take an eVolt and land it directly onto an 8 kilowatt battery inverter, and then the money that you normally be spending on combining material, instead it's going straight into the battery. So you're getting more bang for your buck with the eVolt. Okay, so why would you use the eFlex instead of the eVolt? Well, here's an example where they wanted to put the batteries on the wall, the E vault is really too heavy and large to be wall mounted. So maybe you're in a small room or a closet space and you don't have much space to stick out in front of your electrical equipment. You don't have the space for the E vault to go right off to the side, but you have plenty of wall space. That would be an instance to use the E flex. The E-Flex has a more robust environmental rating. And so if you're putting your batteries in a dusty barn or a porch where it's going to get humid, having that extra environmental protection from dust, humidity, and temperature is an advantage of the E-Flex. And so you want to spend a little bit more money for that. More pragmatically, there's getting the E-Vaults down the stairs. Each E-Vault weighs about 500 pounds, which is about over the limit of your manual stair climber dollies. And so, you get into having motorized dollies to go up and down the stairs with this heavy of an object. And maybe you're not at the point where you're ready to buy or rent a motorized dolly for your installation. And so if you can get all the E-Vaults down to the basement, it's going to be a more simple install, maybe a little more cost-effective install, but you just might not have the ability to get the batteries to where they need to go in an easy manner. And that's where the wall mounting capability of the E-Flex comes into play. And so definitely, when you get into larger systems, using larger batteries will, even though you will have to do some combining, larger batteries, larger systems will simplify the installation. But then there's also environmental reasons or physical access to say you want to break the battery out into smaller components and use the E-Flex instead of the E-Vault. Finally, kind of our last rack, our last mounting option is this rack mount. And I would say don't do a rack mount just for the sake of using a rack mount. So here we have a rack mount with 4 E-flexes inside, and it looks really good and professional to begin with. But I have to caution you, server racks that are rugged and heavy enough to hold this much weight are far more robust than your standard cabinets. And so they cost a lot more money too. And so server racks make a lot of sense when you have a really tall server rack and you're doing a bunch of E-flexes like in a commercial, server room. Or if you have the need for a server rack. The server racks are not for just holding batteries. They're for other kinds of server rack mountable equipment. And so if you have the need for a server rack, it is a nice option. But don't discount, the fact that 3 E-flexes in a small server rack is very similar in form factor to 1 E-Vault. And so while the E-Flex does have is a little bit ahead in terms of Wi-Fi and communication features, it is often a little bit more of a costlier install than just using the E-Vault. And so if the E-Vault can fit on site, if you're not in a humid environment, if you're not in a dusty environment, the E-Vault indoor, great battery, cost effective. If you need a little bit more of a rugged environment or a little bit more of a specialty application, or the room is a little bit small and you have to fit things on the wall, that's when the E-Flex comes into play. And so don't forget our YouTube channel. We do have, installation videos. This is actually for floor mounting the E-Flex. And if you're stretched on budget, floor mounting the E-Flex is about as cheap as it gets. You can build a cabinet around the batteries to protect them. But this is a little wall mount bracket that we have. Essentially what it does is it prevents the E-Flex battery from tipping over. so that you can put it against a wall, and if someone accidentally knocks it or an earthquake happens, the battery doesn't fall over. And so you just kind of get the impression there that floor mount bracket is there for stability. The wall mount bracket, I think, is a little bit more flexible than what initially meets the eye. And so this wall mount bracket actually has some room and spacing to get these brackets right where they need to be. And it can mount the battery upside down as well as right side up, which can be deployed for craftier and better looking cable management. And so these are just hooks that go on to the back of the eflex. With a mounting bracket that you can place, wherever on the wall. And then the batteries get, just hung onto it. And so this actually gives you a little bit more lateral flexibility, which isn't always useful, but I do think it's kind of nice that rather than have a square plate with less flexibility, you get a little bit of wiggle room on your vertical mount location. And I don't know the specific application where that additional flexibility is useful, but it's there for you to have. So with that, we're kind of blown past our presentation hour. So I think when we do our retake of this a month from now, we will have it scripted and a little bit more concise and on point. But this is another good time for questions, and for the audience members who've stuck around, we will go in through questions. Otherwise, I'm gonna go ahead and post the certificate request form in the chat box. And so you should see that now. Not quite yet. Come on, where's my chat? There you are. So in the chat, you now should have, come on, what's going on with my computer? And guys, I've actually moved up to Southampton over the last couple days, so I'm a little bit rough around the edges today. But there you go. Now you have the form for the chat link. Fill that form out if you want a NABCEP continuing education hour, and the certificate will be emailed to you within 24 hours. So with that, I'm going to get into kind of open-end question Q&A, and I'm going to go for the on-topic questions first, and then we'll get into the off-topic questions right after that. Okay, so David Pham, I'm going to get to your question a little bit later. Drew, most of the time the 8 kilowatt inverter is running at 3 kilowatts, so no problem if the amps are exceeded occasionally. Yes, that's right. Our batteries do have the ability to exceed what we call on the spec sheets. You'll get a maximum amperage and then a suggested amperage, and that is true of all batteries. You're going to have maximum temperature ranges and suggested temperature ranges, and you'll have maximum charge and discharge currents and suggested charge and discharge currents. And generally how it works is the warranty that 10-year warranty, that 6,000 cycle warranty is also pegged into staying within the suggested operating ranges rather than the maximum operating ranges. And what that is to say that hey, there are applications where 6,000 cycles is not the bar that makes or breaks the project. It's a more rugged operating condition, and they just need a battery that'll work and can handle the operating environment and can be charged and discharged really quickly, and maybe 3,000 cycles is acceptable instead of 6,000. And so you have the maximum temperature ranges and the maximum operating ranges versus the more constrained settings. Now, deviating from those more constrained settings occasionally is all right. It's that if we are looking at a warranty issue and we see that the battery is operated on a more aggressive charge or discharge at a more aggressive temperature range on a frequent basis, that's when the warranty issue becomes, well, you're using the battery outside of its recommended range, and so it's going to have a shorter life. But a few cycles, a few times is not a problem. Alan, can I use one eflex with the Solarc 12K if I set my max discharge current below 60 amps? I just won't use all the rated output. The answer is you're going to run into those other issues like inrush currents on startup and shutdown, and so it won't work. So the minimum number of eflexes that we warrant with the Solarc is just 2 eflexes rather than 1 eflex. That might be something that we change in the future, but for the most part, the problem is when you start to get too aggressive with the minimum battery bank sizes, you run into other performance issues where maybe a well starting up will trigger the BMS protection, or just turning the inverter on can trigger the BMS protection. So you just run into other issues, and check our website or call our support line if you want to talk about minimum battery bank sizes. So Alan says, where does one find the inverter inrush current spec, not the same as the inverter output surge capacity? Some battery manufacturers recommend spec or current limiting electronics for this case. It's going to be similar to the 5-second or 10-second output rating, surge rating of the battery. So I would just stick within the 5-second or 10-second surge rating or the 10 millisecond surge rating, Alan. Pete says, can the Fortress BMS, so we already covered that one. Janelle asked, will a recording be provided? Yes, but what we're doing with these recordings is we are going through a little bit of an editing process so that the recording that you'll have access to will be even more refined than this webinar today. So just stay tuned, look for our next email updates sometime around December. We'll have finely polished recordings of these programs. Let's see. I have a client that needs, okay, so now I'm getting into some generic questions. So Jane says, can you explain more details on starting up the system slowly with undersized batteries? Basically what the trick is on startup, installers can get really crazy with turning the breakers on very quickly. Breaker, 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 battery disconnect, battery disconnect, battery disconnect. When you get into smaller batteries, short duration batteries on high powered equipment, Whether or not we're managing that through just the battery itself having a high inrush rating, or we're managing that by, such as on the eVault where we have a pre-charge circuit, the solution is to take it slow and leave a few seconds in between each disconnect flip. So when you're turning on our eflexes for the first time, we recommend, they have lights that flash, and we recommend waiting for the eflex to go through its entire diagnostic before you turn on the next one. Similarly with your inverters, just leave a few seconds between turning them on all at once rather than doing it a little bit slowly. When you're starting up slowly with one inverter rather than with one undersized battery, the first pass solution is to say, well, that's why you don't put too small a battery on too large of an inverter. The second pass solution is to say, well, does the inverter actually have two breakers, and is it actually two smaller inverters into one larger inverter package? And then the final Hail Mary pass is to actually turn the inverter breaker or charge controller breaker to flick it multiple times and try and stagger out that inrush current between multiple flicks of the breaker. And so by that point, you're probably giving us a call to begin with, but that's what's happening if we tell you to to kind of toggle the inverter breaker on and off real quickly. It might be to get over that hurdle. What about the enhanced grid support on the Schneider? This is a backup situation where the inverter pulls some watts from the grid when the load is over those watts being provided by the solar modules. Any comment on this in particular? Jose, our manual says to disable the enhanced grid support on Schneider. And so for right now, just keep it disabled. If you have a specific need for using the enhanced grid support mode with the Schneider, send us an email and we'll give it a little bit more attention. Copies of the presentation are available. You can access the dealer resources page on our website to get copies of the slides and programs. So we do provide them to our installers. And again, there's no cost with signing up for that dealer program on our website. Have we tested Fortress batteries in hot and humid climate conditions? What would be the impact of temperature and the battery performance? Most specifically, we are concerned with cold temperatures rather than hot temperatures. If you're in an environment that regularly gets down to below freezing, it is best to put a heating element that only turns on during those times wherever you're keeping the battery to keep it warm. And that can sound like a daunting task. It might be, if your batteries are being kept in the garage, just building a little box for your batteries, running an AC circuit, and putting a very small heater, thermostat heater, in that battery box is all you need to do. When you're mounting the batteries outdoors in a cabinet, there are DIN rail mounted heaters you can buy. For humidity, there's a couple of different things that can destroy a battery life. Temperature is only one of them. Humidity and dust are the others. So when you are installing in a hot and humid environment, that's when you use the eflex, which has that IP65 rating for not allowing humidity and dust to get into the battery. In a hot operating environment, it's not so bad. So if you want a little bit more information on our testing of that, you'll just have to send us an email, and I'll pass you on to our director of engineering. All the install costs and details need to be reduced to a single plug. Why can't I get a 60 kilowatt hour solution with a bolt that includes a free car and computer, etc.? Um, you know, I get it, Drew. I want these solutions to be as cost effective as possible too. I don't think it gets any more cost effective than using the e-volt. And so if the goal is cost effective solutions, I would look towards the e-volt. When you start getting much heavier than that, it starts logistically. You need to divide up the battery before it gets to the site. And logistically, buying multiple small things is going to cost more than buying one large thing at the same time. Can I connect them in series for higher voltage systems? No, you cannot connect our batteries in series to increase the voltage. So right now we're supporting the 48 volt platform. We are coming up with a higher voltage commercial system early next year. As far as high voltage residential, it's on the horizon, but it's not one of our short-term priorities. So don't try and create your own high voltage battery by wiring them in series. That won't work. So Adam says, at what point do multiple charging resources start to interfere with voltage readings for each other? Anytime you're charging the battery, the circuit's going to be at a higher voltage than what its resting voltage is. And so you might be dealing with a battery that's dead, but it has enough in it for the sun to come up and the charge controller to come on, and then you're reading the battery voltage. You're like, oh, this is at a high voltage. This is at a healthy state of charge. If you turn off all the charging resources, that voltage drops way back down. So anytime you're charging the battery, the voltage readings can start to, maybe indicate a healthier battery than what you have in terms of resting voltage. Is there a battery amp hour to charging amp supplied relationship to determine, if the battery was at a higher voltage range while charging, what the battery will just drop down to in terms of voltage rating? It's very difficult to determine that. That's where when you get into closed loop communication with battery management system to inverter communication, it flips over to state of charge control. But state of charge control requires computer calculation. It's not something that can be done with pencil and paper. The state of charge controls factor in individual cell voltages, temperature, humidity, and use. And so that's really just something you get with a computer driving it rather than a hard code setting. So that's where you have state of charge controls with closed loop communication, and then it reverts right back to voltage based controls with open loop. The voltage range of a battery is like a plateau in the middle. It's flat, and so it's very hard to say. It's a lot easier to say a battery is fully charged or a battery is at a 20% state of charge or less by monitoring voltage. Anything in between is going to be a function of the battery innate voltage and state of charge plus whatever charging currents are being applied, plus the load. So it's site specific, unfortunately, because that makes it complicated to determine what the battery true state of charge is when it's at 40 to 70%. Will White says, with a battery backup system, how do you calculate the life cycle cost so you can compare a more expensive lithium ion battery to a less expensive, shorter lead acid battery? Will, you might get a little bit more info from that from our first 1 hour webinar. There are benchmarks that you can do to compare battery costs to one another, but generally that will interfere with the end of life of the battery itself and the natural degradation of the battery itself. And so what I would look at first and foremost is the warranted life. And that's because you might get a battery that has a 10,000 cycle rating and a battery that has a 6,000 cycle rating, and they both have a warranty for 10 years. So is the 10,000 cycle battery rating, 80% better than the 6,000 cycle rating? The answer is no. They both have a 10-year warranty, and that's indicative of a 10-year life. And so are you going to get the 10,000 cycles within 10 years? No. Will the battery last longer than 10 years? Yes. But fundamentally, there's other things that are going to degrade that battery, that 10,000 cycle battery, if you're doing one cycle per day, and it has a 10-year warranty. You're like, well, wait, with 10,000 cycles, that's going to give me a 30-year battery. That battery's not going to last 30 years. And so when you go and do a pure cycle cost calculation, you might find that lead acid costs 25 cents per cycle, and lithium ion costs 12 cents per cycle, and you can conclude, lithium ion has half the cycle cost as lead acid. That's more like a laboratory benchmark comparison test. That's not necessarily the exact dollar figure you'd put on it for field testing. Generally what we say is, if it's a daily use battery, you want to transition into lithium technology and away from lead. It's not to say that there aren't applications for lead acid. Generally speaking, with lead acid, particularly with undersized, smaller backup lead acid banks, you'll get into power quality issues if you use them all the time. And so generally speaking, lead acid for backup is a battery that you're not going to be using, that'll just sit there and hang out purely for backup purposes. Whereas with lithium ion, you get into a low enough cycle cost that you can use it to overcome issues like bad solar buyback rate from the utility or extreme time of use metering scenarios. So we have a charging question. If your batteries are being used in a grid tie UPS scenario, where they will sit at the 54.4 volts for long periods of time, should you perhaps set the 54.4 a bit lower and then maybe use the equalization charge to charge them fully periodically? Also, should they be cycled periodically? So Pete, that's a great point. You do want lithium ion batteries to cycle periodically. You don't want lithium ion batteries just to sit there and discharge. So they will last longer if you are cycling them periodically. Now, if you're cycling them frequently, they're going to last shorter. But compared to a daily full cycle versus just sitting there not being used for 10 years, the full cycle battery, granted, we have a 6,000 cycle warranty. So if you're cycling it in 10 years, whichever comes first. So if you're cycling it once a day for 10 years, the 10-year mark will come first, and your battery will last much more healthy. Compared to a battery that just sits there unused for 10 years, the battery that sits there unused for 10 years will have the shorter life versus one that is used within its specifications. So in a UPS grid-tied scenario, you still may want to plan some cycling of that battery periodically. I would still, be programming it to have the bulk and absorb charges rather than use the equalization charge. But effectively, if you set the equalization charge to 54.4 and manually enable it, you're doing the same thing as applying a bulk charge. All right, Drew, less time on the first 30 minutes, second 30 much better. Thanks for the feedback. Michael, if you didn't get a certificate from the last session, you probably filled out that form wrong and didn't give us your right email address. So I don't want to accuse you of being butterfingers, but if you just send us an email at techsupport@fortress.com or send me an email at johnc@fortress.com, that'll come in. If you don't get your Q&A answered, we do have all these questions, so we will send you an email with your question to make sure you get answered. So if we haven't gotten to yet, go ahead and jump out. So Tim Usician says A&L fuses are typically only rated for 32 volts, so that's a good catch, Tim. You know, again, when you're being too cheap with your BOS, you need to check the ratings, because there's a lot of stuff out there that's used in low voltage applications. Their definition of low voltage would be 12 or 24 volt. Jose, you know, another certificate request. Actually, the way that we issue the certificates, the software we use uses my personal Gmail rather than my Fortress. It has the rule apply to at the Fortress, but you may want to check your spam filters, because we send those out all at once. And if you don't get it at all, you know, give it 24 hours. If you don't get it, send me an email and I'll get you a certificate. Okay, Ivan, you have many times I say make sure the battery is at least double the size of the inverter. Based on what we said, that's not always the case. So Ivan, the rule of thumb, if you want a well-sized battery that is not going to run into design issues, the rule of thumb, down and dirty, minimum battery bank size is to take the inverter continuous output, multiply by 2, and that gives you, you know, the good size for your battery bank. So if you have an 8 kilowatt inverter, you want a 16 kilowatt hour battery bank. It's not a coincidence that the E-volt is 18.5 kilowatt hours. You know, that's well sized for an 8 kilowatt battery inverter. But like what I said is, it's not always the case. So for example, we are officially supporting our closed loop communication between Fortress and the eflex, and the Fortress is an 8 kilowatt inverter, and we put 2 eflexes on it, which is 10 kilowatt hours or 11 kilowatt hours of batteries. And the reason why you can get away with such undersizing is that in closed loop communication, we are much more precisely controlling the individual cell, you know, charge and discharge rates, and not just looking at it as a combined 54.4 volts and you're done, but have other triggers that will control, you know, when the charge is cut. And because we're more precisely determining when the charge is cut, we can also apply more aggressive charging and discharging than you could do without that. It's like driving with a full brake pad versus driving with brake pads that, you know, are really on the skids. And so if you want to get into smaller battery bank, minimal battery bank system design, then I suggest going with a closed loop communication system. You know, right now we have the eflex and the Solarc. What's also working right now is the eflex and the Schneider system. That has been a little bit more of a struggle for us to get going, but it is working. And you'll start to see, now that we got that cleared, some more closed loop communication underway. You know, we know that Outback and SMA and Magnum are high priorities. We're also looking at Victron as well. So you should be able to get away with smaller battery banks with those manufacturers in the very near future. So could you not compare a small battery like 1 eflex with a Connex inverter like 6.8 kW? or would you downgrade or go for an additional eflex or go for an LFP10? I would, from here on out, only use eflex and evolts and not use the LFP10s. We, at least from technical support, we're still selling LFP10s and they're still available, and a lot of people are buying them because they either have LFP10s already or they just want the capacity and want to hit the tax deadline. But really, in terms of long-term strategy, the eflex and the evolt are our products that you want to start getting behind. Mainly the eflex and the evolt have better battery management systems than the LFP10. And so now you're saying, can we get away with just one eflex? We recently just moved to 2. And so what we're seeing on a technical support side is a decent amount of technical support issues where customers have too small a battery on too large of an inverter. So you probably won't have us support one eflex on an inverter that large anytime soon. So if you want to get away with systems where you're just buying one eflex and that's it because of budget, then you need to drop down your inverter size. I'm not even sure that we officially warrant the one eflex on even a 4 kilowatt inverter. I think if you want to do one eflex, what I would look at is the Victron Easy Solar 2, which is a 3 kilowatt inverter, and we would support that. Let's see. Can we install 2 evolts on one Solarc? So yeah, absolutely. So I guess Burgess, you've left. I'll have to email you that one. Oh, you're back. Yeah, you can put 2 evolts on a single Solarc. The 2 evolts on a single Solarc are going to give you really good home backup capability. Probably over a day's worth of storage. You could also down the road add another Solarc to that and not have to increase your battery size. So if the homeowner wants to put their whole house on the backup side, maybe 8 kilowatts or 12 kilowatts grid tie, 8 kilowatts off grid isn't quite enough power, you could do 2 Solarcs. The nice thing about starting with one Solarc and 2 evolts is you can always add more inverter capacity if you need it. So Adam says, is it healthier not to fully charge the battery and then to manually start a shortened bulk charge? I don't think you need to worry too much about the bulk versus absorb. With our batteries, it'll bulk charge all the way up to the batteries hitting 54.4 volts, and then it'll absorb for about 1 hour afterwards to make sure that all the cells are fully charged. As far as charging it all the way up to 54.4 volts, that's not quite the full charge of our battery anyway, so I wouldn't worry about that. I just charge it up to 54.4 volts and really for lifetime, you can even check our warranty settings, but you can do a depth of discharge down to 20%, which is about 51.2 or 51.3 recharge voltage, and if you wanted to drive it all the way down to 90% instead of 80%, you would get fewer cycles under warranty. All right, so we're over time. None of y'all are gonna insult me by ducking out. We're already kind of at the end of the Q&A. let me see if there's questions I haven't. Will communication with Schneider be released in the next few days? Edwin, it comes down to, are you going to do it on the eflex or the eVolt? With the eflex, we need to upgrade the integration guide for the manual, but that will occur in the next couple of days. With the eVolt, it's a little bit more complicated. The BMS systems are slightly different from each other, and we're still testing with the eVolt, and you may need to upgrade the firmware of the eVolt. So give us a tech support call. We'll get you taken care of, Edwin. But with the eflex, with the Schneider Pro, as long as you have a gateway, we should be able to get you working tomorrow if that's what you wanted to do. Okay, let's see. David Pham, I think you just left. If there's, for the true battery nerds with plenty of time on their hands, feel free to stick around. I'm just going to make note of these questions. They say, we have a 300 kilowatt solar array and a 400 kilowatt battery inverter with a 100 kilowatt diesel generator backup. How would you do that project? I would use SMA. They have a great scalable solution for generator controls. And so I think that they have good products for that. So for kind of off-grid diesel powered man camps, I would look at the SMA product. And furthermore, next year, our eVolts are going to be much more stackable than they are now. So you'll be able to get up to that. Right now, we only support up to 222 kilowatt hours of battery capacity, the eVolt. Next year, we will be increasing that. So 400 kilowatt hours is not going to be a problem. Let's see. Other questions. So with that, hey, it's not only is it 5 o'clock somewhere, it's 5 o'clock right here on the East Coast. So we're going to be calling it to a close. Michael says, do you need a gateway for closed loop communication with Schneider? You do. You have to use, we're only testing it with a gateway. You're actually wiring the closed loop into the gateway rather than into the Schneider itself. I'm not sure how that would work, just going directly to the Schneider and bypassing the gateway. If you're using the COM box instead of the gateway, I don't know if we're officially supporting it. I've looked at the COM box. It does have the RJS485A and B inputs, so it might work with the COM box, but we can't guarantee it yet. I don't know if we will ever guarantee it. If you want to play around with it, give us a call. And right now is a good time to explore issues like that, because we're still, troubleshooting, doing research and development ourselves. We're not so busy that we can't, help you with your pet projects at this time. Maybe next year, 2 years, the battery industry grows to the point where we don't have as much time to support that. Hopefully we will, but now's a good time to give us a call on issues like that, Michael. Okay, so with that, I hope everyone has the quiz link. If not, I'm sure I will hear from you for getting the certificate, but otherwise you have a good rest of the day, and stay tuned for future webinars. Provide feedback. It'll help us, spend more time on the topics that you need. And with that, don't forget in round 2, we will be offering these again. And, first time through, it's always fun. Maybe you get the content a little bit more specialized. Second time through, a little bit more disciplined, and we'll have some nice comprehensive handouts for you.